Good morning. Today we're going to talk about section 4.9, antiderivatives. And the entire premise about this is if we perform differentiation, can we undo what we've just done? Can we do the opposite of differentiation? And the answer is yes, and we simply call it anti-differentiation. Anti as in opposite. So the goal of differentiation is to find the derivative f prime of a given function f. But we can also perform the reverse operation. That is, given a function f, we can find the antiderivative capital F such that capital F prime is equal to lowercase f. So here's a definition. A function capital F is an antiderivative of little f on an interval I provided f prime of x equals f of x for all x in I. So let's think backwards for a moment. Consider the derivative formula d dx of x equals 1. It implies that an antiderivative of f of x is 1. That is, capital F of x is x, because capital F prime of x is f of x. Using the same logic, we can write d dx of x squared equals 2x as an antiderivative of f equals 2x is capital F of x equals x squared. So if we can go forward, we can always go backwards. So here's another question for you, and go ahead and think on this. Does a function have more than one antiderivative? Go ahead and spend a moment or two thinking about what this question could possibly mean, and then continue on in a moment. So consider lowercase f of x equals 1. Our antiderivative could be capital F of x equals lowercase x, or capital F of x equals x plus some constant c. And c is going to be real valued, so no i's, no imaginary numbers. It's got to be a real number, but it can't depend on x. In either case, when we take the derivative of capital F of x, we get lowercase f of x. But what does this mean exactly? Let capital F be any antiderivative of lowercase f on an interval I. Then all of the antiderivatives of capital F on I have the form capital F plus c, and c could always equal 0. And c is always an arbitrary constant. And we call this a family because if I said x plus 1 or x plus 10 or x plus 70, when I take the derivative, I'm just going to get the value 1. So the value 1 has infinitely many antiderivatives. And there's specific ways to solve for them, but we're going to cover that a little bit later in the term. So let's use what we know about derivatives to find all the antiderivatives of the following function. Lowercase f of x equals 3x squared. So go ahead and think backwards. You've got a little bit of a hint, and we know that we want to go the opposite direction from differentiation. So we know that x squared should probably turn into x cubed. But what do we do about the constant? So using what you know about derivatives, you might say that we just pull the constant out in front and make it our power, and you'd be pretty close. And you can see here that the antiderivative of 3x squared is x cubed, and every antiderivative just means that we're including this plus c. Now this plus c is a very important character, and you're going to want to include a plus c anytime you've got an indefinite integral, and I'll talk about what that means in a moment. But anytime you're taking an antiderivative, you're going to include a plus c. That way you know you're correct no matter what you do. Emphasis here, if you leave off a plus c when you get to Calc 2, they will take points off. How do I know this? Because I was a Calc 2 TA and I took points off. So make sure you're always writing a plus c. If you don't remember anything else from this class, I hope you remember that. So this one's a little bit more of a challenge. Use what you know about derivatives to find all antiderivatives of the following function. F of x equals 1 over 1 plus x squared. And you might think, Emily, this is really hard, but go ahead and give those trig different derivatives one more look-see, especially tan, cotangent, secant, cosecant. Take a gander at those and then come back to me. So again, this one is a little bit more challenging, but we recall that d dx of tan inverse of x is equal to 1 over 1 plus x squared. So the antiderivatives of f of x are capital F of x equals tan inverse of x plus c. And again, we're including this plus c because we want to find all the antiderivatives of the following function, not just one particular solution. So finally, use what you know about derivatives to find all the antiderivatives of the following function, where f of t equals sine of t. And just like before, just because we've changed our variable from x to t doesn't mean that we fundamentally changed what I'm asking you to do. I'm just asking you to go backwards. So recall that ddt of cosine of t equals negative sine of t. But we're looking for a function whose derivative is sine of t, not negative sine of t. So observe that if I pull a negative out and I go ddt negative cosine of t, well, my negatives are going to cancel out on the right-hand side and I'm left with sine of t. So it follows that the antiderivatives of f of t are capital F of t equals negative cosine of t plus c. And again, we're including this plus c because it's fundamentally very important. So now let's talk about notation, and you'll understand why I use the term integral in just a moment. We use the notation ddx of f of x to mean take the derivative of f of x with respect to x. So there's got to be a notation for find the antiderivative of a function f of x with respect to x. And in fact, it's these symbols right here. We have a big stretched out s, our function f of x, and then this little guy dx that you maybe remember seeing earlier in the term. And anytime an indefinite integral sign, this bad boy, appears, it is followed by a function called the integrand. So f of x is your integrand. And then by the differential dx. The integral sign tells you to take an antiderivative, while the integrand tells you what you're taking the antiderivative of, and the differential tells you with respect to which variable. So antiderivative and integral mean the exact same thing. We're finding the integral of a function, or we're finding the antiderivative of a function. And regardless of what I ask, you're performing the exact same steps. So this notation is very important, and you'll see it a lot more as we go through the rest of the term, and you'll see it continually through Calculus 2 and Calculus 3. The premise of being able to take derivatives is maybe the first half of calculus, and it's very important. The second half is being able to undo that, so being able to take integrals or to find antiderivatives. So calculus is more or less made up of two parts, and you've already seen the first part, so now we're just introducing you to the second part. So let's work on an example so you can get familiar with the notation. The integral of 3x squared times our differential dx is x cubed plus c. And you'll remember that I could have written out, find the antiderivative of 3x squared, and it equals the family of solutions is x cubed plus c, or we can just use our notation and write it out like this. So now let's give you some rules so you know what to do. For p not equal to -1, the integral of x to the power p dx is equal to x to the power of p plus 1 over p plus 1 plus c. Now, what about a constant multiple rule? Say my function is 5x. So my function is x, and I've got a constant 5 multiplied out in front. Well, I'm welcome to just pull that constant out in front for all real numbers c. This will not work if c is a function that depends on x. This only works if it's a constant multiple. And finally, here's the sum and difference rule. The integral of a function f of x plus a function g of x dx is equal to the integral of a function f of x dx plus the integral of a function g of x dx. So let's go ahead and get some practice using these tools. So determine the following indefinite integral. And I've got z squared plus 1 times 2z minus 5 as my integrand, and my differential is dz. That means we're treating z as our independent variable. Z is what we're taking the integral with respect to. So let's work this together. My first step is to multiply out my product of functions. And I get 2z cubed minus 5z squared plus 2z minus 5 dz. Then, using the sum and difference rule, I'm going to split these up from one integral into 4. Then I'm going to use my constant multiple rule to pull out my constant. Finally, I'm just going to use the power rule. Z cubed becomes Z4, Z to the fourth over 4. 2 divided by 4 is 1/2. Z squared becomes Z cubed over 3. 5 divided by 3 doesn't reduce, so we leave it alone. Z becomes Z squared over 2. 2 divided by 2 reduces to 1. And finally, 5. We can think of that as 5 times x to the 0, or 5 times 1. And in that case, we've got 5 divided by 1 times z to the power 1 plus c. And we can check our answer by differentiation. So if I were to take this function that I've written out here, I could always apply differentiation with respect to z, and I'll get out this line right here. And that's pretty neat. You've got a built-in way to check for your answers. So let's continue. Here's some common trig functions, and the integral of cosine is sine plus c. The integral of sine is negative cosine plus c. The integral of secant squared is tangent plus c. The integral of cosecant squared is negative cotangent plus c. The integral of secant times tangent is secant plus c. And the integral of cosecant cotangent is negative cosecant plus c. So here's an example, and I want you guys to work these examples on your own, and in the next slide, I'll just give you the solution. So determine the following indefinite integral. I've got 2 over pi sine of x minus 2 cosecant squared x, all dx. So x is our independent variable. I've got my integrand function, and I've got an integral sign. I've got all 3 things I need to make this work. So go ahead and give this one a test and see if you can't figure out what the solution should be. The solution is 2 cotangent x minus 2 over pi cosine x plus c. If that's surprising, check that table again or send me an email. Now, here are some other functions, not trigonometric, but just other functions. If d dx of e to the x is e to the x, then the integral of e to the x dx should just be e to the x, and we find that that's true. Now, conversely, we get that dx over x integral is equal to the natural log of x plus c. That might be surprising to you, but this is one you're just going to have to memorize. Dx over square root 1 minus x squared integral is sine inverse of x plus c. The integral of dx over 1 plus x squared is tangent inverse x plus c. And finally, the integral of dx over x times quantity square root x squared minus 1 is secant inverse absolute value of x plus c. So go ahead and just write these down, and you're going to just have to memorize them. So here's our final example for the day. Determine the following indefinite integral as given. And this is the integral of 4x cubed plus 2x divided by 3x squared dx. And you might be saying, Emily, this is really hard. We don't know how to do this. Well, let's go ahead and take our first step, which is always to simplify. So my first step is I've only got one term in my denominator, so I can split it up. So now I've got 4x cubed over 3x squared dx plus the integral of 2x over 3x squared dx. I'm going to reduce powers from my x's, and I'm going to pull my coefficients out in front. I go ahead and I take the integral, and I get 4/3 times x squared over 2 plus 2/3 natural log x plus c. Well, 4/3 times 1/2 is 4 over 6, which is the same as 2/3. So I've got a 2/3 in each term, and I pull that out, and I'm left with 2/3 times quantity x squared plus natural log of x plus c. And that's it for me today.